Hello, everyone. I'm Ivan, and I'm going to talk about high-performance GPU to CPU transpilation and optimizations via high-level parallel constructs in Polygeist and MLIR. And basically, our aim is to compile CUDA software to run on CPUs and do some optimizations while we're at it. And so use cases of this, obviously we can reuse existing GPU software on CPU-only machines, and this lowers development, porting cost and time, and we can leverage the higher parallelism that GPU software assumes. And an example of what we did is to run PyTorch on a Fugaku supercomputer, and we got very good results with that. And it was a nice added bonus is the ease of debugging on the CPU. So basically, mainstream compilers do not have a very good representation of parallelism, which makes some optimizations difficult. And this is especially true for GPU code, because from the start of the pipeline, they live in the host side code and device side code live in separate modules. So you can't optimize really anything beyond that boundary. And so a short introduction to Polygeist, which we're using, is a C and C++ compiler, which lowers C++ to MLIR, where we can do various optimizations, transformations, which then gets lowered to LLVM, optimize that, and we get binaries. So what we do is to preserve the parallel structure. So we have on the left a kernel, which gets called in a function. And we can actually inline the body of the kernel into the function or the call site where it's getting called, and inside like a parallel loop. And then we can very easily spot some available optimizations. For example, we have a call to a sum function, which does not depend on the thread index. So we are just calculating it for every thread, even though we don't need to. And we can easily just hoist it out of the loop, and we calculate it only once. Another thing we do is represent synchronization within kernels. So basically, synchronization is it ensures that all threads have finished execution up to that point before continuing onwards. And the semantics of this can be represented by defining the synchronizations to have memory effects of like all of the writes and read memory effects before that and after that. And this allows code motion of code that does not write or read any memory. So we can move some index computation. And we can actually do better than that, because within a single thread, the memory semantics are guaranteed by the control flow of the program. So if we index some memory with an index the same way throughout like across the barrier, we can actually remove that memory effect from the barrier, allowing us to poke a hole through the barrier, which we can move code around or forward memory. And another thing we can do is to look at the memory effects before the barrier and after the barrier. And if we see that they don't conflict each other, then that means that the synchronization was not necessary in the first place, which means we can remove it. And after we do that, we have to transform the GPU code to CPU. And because CPU backends don't have an equivalent synchronization operation, a very efficient one, as GPUs do, we have to do something like this, for example, where we have a parallel loop with a synchronization. We distribute the parallel loop around the synchronization point so that we can execute all the code before the point and all the code after it. And some quick evaluation. We get better performance over handwritten OpenMP of equivalent problem by 1.7 times. We get better scaling than OpenMP equivalent program. And we get 2.7 times performance improvement over the native PyTorch CPU backend. And please check out like the more detailed talks on Polygeist tomorrow, and there's SC22 next week. Thank you.